So, are you able to hear me?
Yes, sir.
Okay, good. So yesterday we have discussed about this lasers, introduction to lasers. So we have seen that there will be three distinct processes when light interacts with the matter, right? Yes or no? Hello?
Sir, yes, sir.
Right. So today we are going to discuss about what are the conditions that require for a laser action. Okay, that is or lasing action. So how do we generate light? That is so yesterday we have discussed that laser is not a light, but instead it is a laser. It's a generator of light, right? So how do we generate light using this particular process? So what are the conditions that require for this lasing action? So that we will see today. Okay. So just before going to that, we'll just review what we have discussed yesterday. So today the topics we are going to cover is population inversion, metastable state, and lasing action. So we expect you to understand the conditions that required for lasing action, and this aligns with our course outcome CO5. So when light interacts with radiation, we have seen that there will be three distinct process will happen. That the first one is absorption, second one is spontaneous emission, and third one is stimulated emission. So what are these three processes? So when light radiation interacts with matter, there will be energy absorption, that is energy is given to the atoms, or atoms gives energy to the radiation. So these two things are different, but we can as we discussed yesterday, the second one, that is atoms giving energy to the radiation or to the light, is not explainable with the help of classical mechanics. But to understand that particular process, we need to understand the quantum process. Okay, there will be quantum mechanics involved in this. So that we have seen yesterday. So we just review that. So what is an absorption? Absorption is when a photon of energy incidents energy h nu incidents on the medium, an atom residing in the lower energy state even may absorb the incident photon and jump to the state E2. That is, just see this the graphic. So we consider two energy levels, where one is E1 and another one is E2. Okay, so when a photon is incident on the medium, then the atom residing in the lower level absorbs this photon and a photon energy and moves to the higher energy level E2. This is possible only when this photon incident photon energy equals to the difference between the energy levels, that is E2 minus E1. Okay, so this particular process is called absorption. So yesterday, as I said, this moving jumping of atoms from one state to another state is called transitions. Okay, so these transitions, this transition is particular transition is called stimulated absorption. That is because photon is absorbed by the atom and moved and jump to the higher state. Okay, so the second process here is also, before going to that, so we have seen that the probability that an absorption transition occurs is proportional to the photon density rho of nu. Okay, so this makes sense, right? So how many, if there are many number of atoms in the lower energy levels, and if there are sufficient number of photons incident there, then there will be more number of atoms will be jumping to the higher level, right? So if there are more number of photons, then more number of jumps. That is the probability that absorption transition occurs only is proportional to the rho of nu. So that is, we have taken P1, 2, that is P stands for probability of absorption, and 1 to 2 is for from one level, from the first level to the second level, is proportional to rho nu, and P1, 2 is we have taken it as B1 to rho nu, where rho B1, 2 is a proportionality constant, and it is called as Einstein coefficient for induced absorption. Okay, now what are the number of transitions that can occur in a particular time delta t? So if we, in a given time interval, how many number of transition can occur in this? So let's say if the number of absorption, suppose if n1 is the number of atoms in the energy level n1, then the probability, the total number of absorption transitions is given by the total number of atoms in the lower level times the probability for absorption, and that is within the interval delta t. Okay, so this is given by, and absorption is given by the product of the total number of atoms in the energy level n1 and the probability for the transition, that is absorption transition, and within the interval time delta t. Okay, so we use this particular expression in our later discussion. So the another process we have seen is spontaneous emission. So spontaneous emission is the excited the excited atoms which are in the higher energy level, due to the absorption, they may not want to stay there for a longer time. Okay, so they will usually atoms tend to have a lower energy. So whenever this absorption process takes place, so the excited atoms don't stay there for a longer time, so they would like to come back to the lower energy states, so that they come back to the lower energy levels by losing some energy. Okay, so this in which form they lose the energy? In forms of photons. Okay, in the form of photons. So this particular graphic that we can understand from here, so as you can see that this particular atom loses energy in the form of photon, that is, and this photon energy is equals to E2 minus E1. Okay, this particular photon energy is given by E2 minus E1 because the energy required to the for the atom to stay in E1 is E1, right? So it loses from E2 to E1, so that for emitted photon energy will be equals to E2 minus E1. Okay, this particular process, that is the type of process in which photon emission occurs without any external impedance, that is without any external disturbance or without any external influence, called spontaneous emission. Okay, so there are two types of emissions. One is on its own, atom on its own loses energy and comes back to the level 1. Okay, and loses energy in the form of photons. Okay, so what is the probability for occurrence? This is, so in on which properties this spontaneous emission occurs, it depends on. So the probability that a spontaneous emission occurs depends only on the properties of energy states E2 and E1, and is independent of the photon density, because here this particular process, this spontaneous emission, is happening because of happening on the tendency of this atom to go back to the energy level E1. Okay, suppose if the energy there is no external influence for in this process. Okay, so it does not depend upon the external force or the external photons that is emitting, that is we are shining on the material. Okay, so it is depends upon the only on E2 and E1. Okay, so this depends upon also these so this depends what is the lifetime of this particular state E2. Okay, if the lifetime is how much time that an atom can stay in a higher energy state or the given higher energy state. Okay, so that is I'm sorry, this is time. So this is as I said, this requires as the lifetime. Okay. Okay. The amount of time that an atom can stay in an higher state is called lifetime. Okay, if the lifetime of this particular energy state is high, then it stays a longer time. If the lifetime of this particular energy level is low, then it stays very lesser time. Okay, so it is equals to the probability that the probability for the spontaneous emission to occur equals to the lifetime lifetime of level E2, that is P21 absorption equals to A21. Okay, where A21 is known as the Einstein coefficient for spontaneous emission and is a measure of the lifetime of the excited state. Okay, now what are the total number of spontaneous emissions that can occur in a time interval delta t? So this is given by the total number of atoms in the energy state E2 and multiplied with the probability of that absorption, probability of the spontaneous emission to occur, and this is delta t, that is the time interval that we observe. Okay, so n spontaneous equals to A21 n2 delta t. So there is third option. There is a third distinct process that can occur when light interacts with the matter, that is stimulated emission. Okay. So the interaction of, so we have seen in absorption, the photon interacts with the atoms that reside in the lower energy level, that is in the level 1. Okay. So there what happens is this energy is absorbed by the atom and jumps to the higher energy level. Here in stimulated emission, what happens is the interaction of photon will be with the atom which is already in the higher excited state. Okay, but this excited states, what happens is, in this process, what happens is this interaction leads the atom to lose the energy and jump back to the lower energy level. Okay, so if you can see this in this graphic, so here the atom is already in the higher energy state, and this interacts with the incident photon, which is having the energy h nu. Then it goes back to the lower energy level by losing energy in the form of a photon, and this particular photon will have the same properties as of the incident photon. Okay, they'll have the same phase, they will be both in the same phase, they'll have the same energy, and they will travel in the same direction. Okay, so this is the stimulated emission. So this kind of forced emission of photons is called induced emission or a stimulated emission. Okay, so the probability that a stimulated transition occurs is given by this P21 stimulated is equals to B21 rho of nu. As you can see that here also, similar to absorption transition, here then amount of the stimulated emission to be occurred, it requires it depends upon the density of the incident photons. If there are more number of photons, then there is a more chance for the higher energy atoms to interact with the photons and lose energy by giving an photon and jump back to the lower energy state. Okay, so P21, so this is this probability is proportional to the density of photons, and P21 stimulated equals to B21 rho of nu, where B21 is a proportionally constant and as known as Einstein coefficient for stimulated emission. So as yesterday we have I have told you that the theory behind the stimulated emission is first proposed by Einstein in 1916. So that's why we call all these coefficients as Einstein coefficients. Okay. So the number of stimulated transitions occurring in the material during the time delta T is given by the total number of atoms in the energy state E2 multiplied with the probability for the transition occur in time delta T. So this is N stimulation is equal given by N2 B21 rho of nu delta T. So basically there are three processes. In one, the energy is absorbed by the atom and goes to the higher energy level. So it jumps to the higher energy level. So that is absorption. Okay, because energy is absorbed. Now, in the other two processes, what happening is this is emission. They are in emission process and photon is emitted. Okay, a photon is emitted. But how it emitted depends upon, it gives you two types of emission. That is, if atom loses energy on its own and jumps back to the lower energy level, that is we call spontaneous emission. Okay, now if the atom interacts with the incident photon and leaves to and jumps back to the lower energy state by giving a photon, that is what we call stimulated emission, because that is induced emission or stimulated emission, because it is occurred due to the incident photon, interaction with the incident photon. Okay, so so far, are there any doubts? Anyone? Can you guys hear me?
Yes, sir.
So are there any doubts?
No, sir.
No? Okay, good. So let's see what are the differences between spontaneous and stimulated emission, because this is why I see absorption process that we are not interested, because the energy is we are losing the energy. But whereas here in emissions we are getting the energy. So photons are emitting, that is light is emitting from the material. So we are interested in this process. So we'll see what are the differences between these spontaneous and stimulated emissions. So in spontaneous emission, the emitted photons are random. So this first of all, this process itself is a random process, because we don't know at what instant we don't know at what instant this atom loses energy and jumps back to the lower energy state. Okay, it completely depends upon the properties of the energy state. Okay, so this is completely random process. But stimulated emission is not a random process. Okay, because we know if you shine the atom, if you shine the radiation, or if you shine with a light, then this process will happen. Okay, now so since this is a random process and the atoms loses energy on its own, we cannot control this from outside. Okay, but whereas the stimulated emission can be controlled from the outside. So we know how to, as long as we increase the intensity, then the more number of photons will be emitted due to stimulated emission. If you decrease the intensity, then there will be less number of stimulated emission transitions. Okay, so this we can control. Okay, now these photons emitted in uniformly in all directions. Okay, so in a spontaneous emission, photons will be emitted in uniformly in all directions. So the emitted photon, the emitted light, so the resultant of these photons will be non-directional, and it will be because of this photons will be emitting in the random directions. The intensity of the photon, the intensity of the emitted light also will be very less. Okay, whereas the photons emitted in the stimulated process will have the same direction of the incident photons. Okay, therefore the resultant wave, the resultant light will be completely directional. Okay, so the spontaneous emission emitted light is non-directional, whereas stimulated emission photons or the light is directional. And here the photons emitted will be slightly different frequencies. Okay, they'll be slightly different frequencies. Therefore, they are not monochromatic. Okay, they are not monochromatic. Monochromatic means all the waves should have a same wavelength or same frequency. Because of this, different frequencies will be generating here, so the light will be not monochromatic. Whereas the spread of the photon frequencies is relatively very narrow, so we can say that in fact it's negligible. It's not even very narrow, we can say that it is negligible, and all the emitted photons will be of the same frequency as the incident photons. So the emitted light is monochromatic. Okay. Also, because the photons do not have any correlation in their phases, because as we can see that the emitted photons will be completely random and they are completely emitted in the random directions. Okay, uniformly in the all the directions. So that's why there is no correlation between the phases of the emitted photons. So the light produced by this process will be completely incoherent. Okay, whereas in stimulated emission, the photons emitted or in phase, and the emitted light is coherent. Okay, coherence means if all the waves are in a same phase, or if they have a constant phase difference, then we call them as coherent. If they do not have the same wavelength, if they are not in same phase, or if they don't have a constant phase difference, then we call them as incoherent. So this is what happens in spontaneous emission and stimulated emission. In spontaneous emission, it is the light emitted is incoherent or non-coherent, whereas in stimulated emission, the emitted light is coherent. Also, the intensity generated will be equals to I into n, whereas n is the number of atoms emitting photons, because the how many number are there in the higher energy states, that and the intensity of the each photon will be the intensity of the emitted light. Whereas as all photons are in phase, they constructively interfere, because here there will be a non-destructive interference also happens between the photons because of the difference in the phase. Whereas here all the photons are in the same phase, so there will be a constructive interference, and they produce the intensity which is equals to n square I, where n is the number of atoms that emits photons, that is the number of atoms in the higher energy state. We can if you're taking it as n2, so we can write it as n2 square I, and where I is the intensity of the each photon. Okay, so I is equals to n square I. So you can see that here it is this it is equals to in, whereas here this is also it. So here the it is equals to n square I. So you can see that this is very high intense. The light emitted through stimulated emission is very high intense, whereas spontaneous emission is very low. Okay, comparatively. Also, the planes of polarization of the photons are oriented randomly, hence the light from the source is unpolarized, whereas the planes of polarization are identical for all photons. Consequently, the light emitted here is polarized. Okay. Now, steady state. Under steady state condition, the absorption and emission balance each other. That is, how many absorption transitions are happening, the same number of emission transitions should happen. Okay, this is what we call a steady state condition. That is, number of absorption, it should be equal to total number of emissions. That total number of emissions includes, that is, spontaneous emissions and stimulated emissions. So number of absorption equals to NSP plus NSG. So we have just written down that this number of absorption transition is given by this expression, that is B1 to N1. N1 is the total number of atoms in the lower energy level multiplied with this B1 to rho nu is the probability times delta T, whereas this is A21 in spontaneous is given by, this is the Einstein coefficient, and this is the probability A21 N2 into delta T. So here this is given by, and stimulated emission is given by B21 N2 rho of nu D delta T. So this delta T will get cancelled. We can just take delta T common and we can just cancel them out. So B1 to N1 rho nu is equals to A21 N2 plus B21 N2 rho of nu. Now, if you consider a medium in thermal equilibrium, there will be more atoms in the lower level than at higher level. So this is what happens, right? So we know that there is all the atoms will try to have a lower energy. So there will be more number of atoms in the lower energy than in the higher energy. Okay, so this N1 will be much greater than N2. Therefore, what happens is the number of transitions occur. So N1 will be very high. So the absorption transition will be more, right? So a photon traveling through the medium is more likely to get absorbed than to stimulate an excited atom to emit a photon, right? Because since N1 is much greater than N2, there will be more atoms will absorb the photons rather than the number of atoms in the higher energy absorbs the interacts with the photons, right? Yes or no?
Yes, sir.
Therefore, the absorption dominates the process of the stimulated emission. Okay. Now, another one is an atom that is at the excited state is more likely to jump to the lower level on its own than being stimulated by a photon. See, the same reason, because there will be less number of atoms in the higher energy state, then there is a more chance for the atoms which are absorbed by, which are excited to the higher energy levels. So they don't have much photons left. So they don't have much photons to interact. So most of the atoms will try to jump back to the lower energy state on their own. Okay. So So here, because this is why, because it is due to the fact that photon density in the incident beam is not sufficient to interact with the excited atoms. So there will be more now, since N1 is greater than, much greater than N2. There are very less number of atoms or less number of photons available for the higher energy state atoms to interact and get stimulated and jump back to the lower energy level. So they usually jump back to the lower energy levels on their own. That is, spontaneous emission. There is a spontaneous emission dominates stimulated emission. Okay, so both absorption dominates the stimulated emission and spontaneous emission dominates the stimulated emission. Why here? Why we are comparing absorption and stimulated? Because absorption stimulated emission requires number of photons, right? So there will be more number of atoms in the lower energy state. That's why there is a high chance for the photons to interact with the lower energy states and gets absorbed to the higher energy state. Okay, so that's how absorption dominates stimulated emission. But whereas the less number of photons are available for the atoms which are in the higher energy state, so there is a high chance for them to move back to the lower energy state on their own. That's why spontaneous emission dominates the stimulated emission. Okay, so is everyone understand this concept? Why absorption dominates stimulated emission and spontaneous emission dominates stimulated emission?
So once can you repeat?
Yeah. So let me draw a figure here. So we have two energy levels. The number of atoms here is N1 and the number of atoms here are N2. So when there are photons are incidenting on this material, there will be, because there are more number of atoms in the lower energy state, so there is a high chance of for the photons to interact with N1. See, usually this N1 N2 their ratio will be N1 by N2 will be of order of 10 power 30. Okay, so there that means the number of atoms in the lower level equals to 10 power 30 times N2. Okay, so there, that's why there is a high chance for the photons to interact with the atoms in the lower energy state and move and jump to higher energy state. That's why this absorption dominates the stimulated emission. Okay, so as all the photons are, there is a high chance for interact with the lower energy atoms. The atoms which are in the higher energy tend to come back to lower level on their own. Okay, they tend to come back on their own rather than stimulated by these photons. Okay, so there are some photons which will be interacts with N2, but it will be very less compared to the spontaneous emission. Okay, because there are less number of photons are available for the higher energy atoms, so they tend to jump back to the lower energy states on their own. That's why stimulated emission is dominated by spontaneous emission. Okay, so did you understand now?
Yes, sir.
Okay. Now, the main process, what is a laser actually? Laser is light amplification by stimulated emission of radiation, right? So how does this light amplification happens? No, since this as just now we have seen that the laser operation is achieved only when the stimulated emission exceeds the other two processes. Okay, now just now we have seen that absorption, that is number of absorption is much greater than number of stimulated transition, and number of spontaneous transitions or greater than number of stimulated transition. But as we have seen that only when stimulated emission happens, only in this process there will be a constructive interference, right? There will be constructive interference, and there will be a constructive interference, and there will be a high intensity light will generate. Okay, there will be high intensity light and high amplification. Okay, because of the constructive interference, we'll get high intense light and high amplified light. Okay, so to achieve this, we have to say that, okay, there is amplification means increasing the amplification means increasing the some particular quantity, that is the amplitude will be higher than the original amplitude. Okay, so stimulated versus spontaneous emission, if you compare these two, n stimulated by n spontaneous equals to B21. We know that n stimulated is given by this expression B21 N2 rho of nu by A21 N2. So that it gives us B21 by A21 rho of nu. This N2 N2 will get cancelled. We are left with this one. Now, to get this, we need this ratio to be very high. Okay. This ratio, we want this ratio to be very high because n stimulated should be very high compared to n spontaneous. Then only we'll get light amplification. So for this process, this is anyway, these are the coefficients, these are constants. So we need high intensity of the high density of the high intensity of photons. Okay. And when stimulated emission, when you compare stimulated emission versus absorption, then this is given by N2 by N1. Okay. Now this, we also want this ratio to be very high. So for that process, we need more number of atoms in the higher energy level than lower level, right? We need N2 must be greater than N1 to achieve this condition. Okay, whereas here we require way more number of incident photons. Okay, so the conditions, so we are the conditions, if you write them in a summary, if you can write as a summary, we need three conditions for light amplification. That is large number of photons. So as you can see here, we require large number of photons, incident photons. And the second condition is states with larger lifetime, states with larger lifetime. So this is another condition here, this A21. So this should be very small, right? This ratio B21, the ratio here B21 by A21, this ratio also should be very high. This only happens when this A21 is small. A21 is small, and the lifetime is usually given by 1 over A21. Okay, the lifetime of a energy state is given by 1 over A21. That means we should need higher lifetime states. Okay, so A21 should be small. That means we need the lifetime of the lifetime of the energy state should be higher. Okay, that is the second condition. And the third condition is N2 should be greater than N1. So these three require these three are the condition that requires for light amplification. Okay. I think it's we'll stop here. So we'll so these are the three conditions that we require for light amplification, and we'll see how we achieve these conditions for lasing actions. So far, are there any doubts?
No, sir.
Okay.
Sir, please can you
Yeah.
explaining once again, sir? Didn't understand that.
Which one?
Light amplification, sir.
Light,
First
ampli-
Yes, sir.
light amplification. Okay. So did you understand this part? Absorption dominates stimulated emission and spontaneous emission dominates the stimulated emission. Hello?
Sir, that one didn't understand, sir. That one also.
This one also you didn't understand. Okay, this now that requires more. Okay, so we'll do one thing. We'll start from here tomorrow. Okay,
Okay, sir.
we'll start from here to tomorrow. I'll explain why how absorption dominates absorption and spontaneous emission dominates the simulated emission, and what we require for the light amplification. Okay, what are the conditions that we require?
Okay,
Okay.
sir. Thank you, sir. Thank you, sir.
So did everyone please whenever from tomorrow onwards everyone please join with your roll numbers instead of your names. Okay, so Uday, Vamshi, Vishal, so you guys please join with your roll number so that it will be easy for me to take the attendance. Okay, and make sure that you are giving your join the roll number, because yesterday I have seen there is some mismatch. There instead of 4, somebody has put 5, but I can understand that by from your mail IDs. Okay, so you will lose your attendance if you have given your roll number properly. If you don't give your roll number properly. Okay.
Okay, sir.
Okay, sir.
Okay. So what is your next class?
Python, sir.
Python. Is Basha sir here?
Yes, sir. Sir, we will end this again. I will start.
Okay, sir. I'll end this. Thank you.